news we read, news we hear, news we share. Year 2038 problem and possible solutions. The year 2038 problem relates to representing time in many digital systems as number of seconds passed since the 1st of January 1970 and storing it as a signed 32-bit integer. Such implementations cannot encode times after 3 hours 14 minutes and 7 seconds Coordinated Universal Time on the 19th of January 2038. Just like the Y2K problem, the year 2038 problem is caused by insufficient capacity of the chosen storage unit. The latest time that can be represented in Unix is signed 32-bit integer time format is 3 hours 14 minutes and 7 seconds Coordinated Universal Time on Tuesday the 19th of January 2038. 231 to 1 equals 2,147,483,647 seconds after the 1st of January 1970. Times beyond that will wrap around and be stored internally as a negative number, which these systems will interpret as having occurred on the 13th of December 1901 rather than the 19th of January 2038. This is caused by integer overflow. The counter runs out of usable digit bits, flips the sign bit instead, and reports a maximally negative number, continuing to count up towards 0. Resulting erroneous calculations on such systems are likely to cause problems for users and other relying parties. Programs that work with future dates will begin to run into problems sooner. For example, a program that works with dates 20 years in the future would have to have been fixed no later than the 19th of January 2018. There is no universal solution for the year 2038 problem. Any change to the definition of the time_t data type would result in code compatibility problems in any application in which date and time representations are dependent on the nature of the signed 32-bit time_t integer. For example, changing time_t to an unsigned 32-bit integer, which would extend the range to the year 2106, would adversely affect programs that store, retrieve, or manipulate dates prior to 1970. As such, dates are represented by negative numbers. Increasing the size of the time_t type to 64-bit in an existing system would cause incompatible changes to the layout of structures and the binary interface of functions. There is also no universal solution for the issue with DVB and ATSC real-time transmitted dates due to issues with legacy receivers. The issue has yet to be acknowledged or resolved by either organization. The only workaround would be to discontinue all time-related metadata services such as programming guides and automatic date synchronization after the affected dates. One possible option would be to create new table types for the affected part of the specifications and use ISO 8601 date strings rather than fixed integers, as are used in ISO 9660 and ISO 13346. File systems. Most operating systems designed to run on 64-bit hardware already use signed 64-bit time_t integers. Using a signed 64-bit value introduces a new wraparound date that is over 20 times greater than the estimated age of the universe, approximately 292 billion years from now. At 15 hours 30 minutes and 8 seconds Coordinated Universal Time on Sunday the 4th of December 292,277,026,596. The ability to make computations on dates is limited by the fact that trademark_year uses a signed 32-bit integer value starting at 1900 for the year. This limits the year to a maximum of 2,147,485,547, 2,147,483,647 plus 1900. Starting with NETBSD version 6.0, released in October 2012. The NETBSD operating system uses a 64-bit time_T for both 32-bit and 64-bit architectures. Applications that were compiled for an older NETBSD release with 32-bit time_TU supported via a binary compatibility layer, but such older applications will still suffer from the year 2038 problem. OpenBSD since version 5.5, released in May 2014, also uses a 64-bit time_T for both 32-bit and 64-bit architectures. In contrast to NETBSD, there is no binary compatibility layer. Therefore, applications expecting a 32-bit time_T and applications using anything different from time_T to store time values may break. Linux uses a 64-bit time_T for 64-bit architectures only. The pure 32-bit ABI is not changed due to backward compatibility. There is ongoing work, mostly for embedded Linux systems, to support 64-bit time_T on 32-bit architectures. 2. The X32 ABI for Linux, which defines an environment for programs with 32-bit addresses but running the processor in 64-bit mode, uses a 64-bit time_T. Since it was a new environment, there was no need for special compatibility precautions. Network File System version 4 has defined its time fields as struct NFS time for int 64_t seconds, uint 32_tn seconds, since December 2000. Values greater than 0 for the seconds field denote dates after the 0 hour, January 1, 1970. Values less than 0 for the seconds field denote dates before the 0 hour, January 1, 1970. In both cases, the n seconds, nanoseconds, field is to be added to the seconds field for the final time representation. Alternative proposals have been made, some of which are in use, such as storing either milliseconds or microseconds since an epoch, typically either the 1st of January 1970 or the 1st of January 2000, in assigned 64-bit integer, providing a minimum range of 300,000 years at microsecond resolution. Other proposals for new time representations provide different precisions, ranges, and sizes, almost always wider than 32 bits, as well as solving other related problems, such as the handling of leap seconds. In particular, TAI-64 is an implementation of the Temps Atomique International Standard, the current international real-time standard for defining a second and frame of reference. News we read, news we hear, news we share.